Hello friends, welcome to my channel. In this video I will cover quick review for strength of material. This is the final video for ISRO 2017 examination. And for slope and deflection I already discussed in a separate video, so you can check it from my playlist. That is also very important. Stress at a point, it represents as sigma ij. I represents orientation of the imaginary surface and J represents direction of internal force. So for 3D stress the matrix is like this: 3 cross 3 matrix, sigma xx, tau xy, tau xz, tau yx, sigma yy, tau yz, then tau zx, tau zy, sigma zz. Here diagonal elements are the normal stresses. Normal stress, sigma xx, sigma yy, sigma zz. Other than this diagonal stress, diagonal elements, others are shear stresses. For one-dimensional stress, one component is sufficient to completely define stress at a point. And for two-dimensional stress, one-dimensional stress, one component. And for two-dimensional stress, four components are required to completely define stress at a point. And for three-dimensional stress, 9 components are required. For two-dimensional stress, the matrix will come like this: tau yx, yy, 4 components, 2 normal stress component and 2 shear stress component. Like this, here also 3 for 3D stress element, 3 normal stress component and 6 shear stress component, total 9 components. And for one dimensional stress, one component is required to completely define stress at a point. A stress component at a point is specified by a magnitude and 2 directions. Stress at a point is a second order tensor. This one asked in IES examination. So this one also you have to remember. Stress at a point is a second order tensor. It will come like this. For 2D stress, sigma xx, sigma xx, sigma yy, then shear stress, tau xy, tau xy. Sometimes they are asking this type of question in IES and ISRO also they may ask this type of question. Stress matrix they will give 90, 40, 40 and 30 and they will ask find the major principal stress and minor principal stress and maximum value of shear stress. All values are in MPa. All values are in MPa. So here we already discussed. This is the matrix given. We already discussed sigma xx, tau xy, tau yx, sigma yy. So from here sigma xx is 90 MPa, sigma yy is 30 MPa megapascal and tau xy equal to 40 MPa. So draw the Mohr circle. First sigma xx, it's 90, then sigma yy, it's 30, take the point at A and B, then midpoint, it will come, total AB is 60, so here 30 30, take the point as center C. So BC is 30 MPa. Then given tau xy, here axis is sigma, you have y, it's 40 MPa. So if you extend this, we will get the radius of Mohr circle. So this point is D. So CDA is our radius of Mohr circle. CD equal to BC square plus BD square root over. So BC is 30 square plus BD is 40 square. So we will get 50 MPa. This is our radius of Mohr circle. So we got CD equal to 50 MPa. So we will draw the Mohr circle. Measure principal stress at E point and minor principal stress at F point. So sigma 1 measure principal stress is C to E. We already got C equal to 60 MPa plus radius of Mohr circle CE or CD value same 50. So 110 MPa. Sigma 2 equal to FC. FC is 60 minus radius of Mohr circle is 50, 10 MPa. Maximum value of shear stress. So tau max we already know, radius of Mohr circle, this is very important. It's 50 MPa. If they will give strain tensor and they will ask to find out maximum value of strain, then you have to take the diameter of the Mohr circle for strain tensors. For strain, 3D matrix will be XX shear strain, this is XY, gamma XY by 2 and gamma XZ by 2. Here YX by 2, YY, gamma YZ by 2, ZX by 2, ZY by 2, ZZ. This is strain matrix for 3-dimensional strain element. You have to remember, for shear strain it will come as half. So we are taking maximum shear strain, it's the diameter of the Mohr circle. When beams are subjected to bending, always beams are subjected to bending stress and direct shear stress. In case of beam subjected to bending in extreme fiber, bending is non-zero and direct shear force or direct shear stress. Direct shear stress, it's 0 at extreme fiber. This is very important. Bending is non-zero and direct shear stress is 0 at extreme fibers in case of beam subjected to bending. And in neutral axis, direct shear stress, it's non-zero and bending stress, this is bending stress, and bending stress at neutral axis it's 0, but direct shear stress it's non-zero. So you have to remember both extreme fiber and neutral axis. So many times asked in IAS exams. And when shaft subjected to torsion, that time shear stress is maximum at outer fiber. Outer fiber and 0 at axis of rotation. Then Maxwell's reciprocal theorem in load and deflection, slope and deflection, for point loads only this is applicable. If the load and deflection positions are interchanged, then deflection will same in both cases. Here cantilever beam is there. We are applying point load W here. Then deflection will get here as delta 1, condition 1, and for second case, if load and deflection they will interchange, means W will come here and delta will come here in this position. So this is delta 2. So from this Maxwell's reciprocal theorem, if load and deflection positions are interchanged, then deflection will same in both cases. Delta 1 equal to delta 2. If load and deflection positions interchange. This is very important in solving problems. They will give this type of figure, W value they will give, and you have to find the delta 1, then delta 2 equal to delta 1. You will get the answer. Here, for shear stresses in beam, the formula is tau s equal to Fs A y bar divided by I into B. Here, take a cross section Mn, and y bar is the distance of CG of this small strip or small area Mn above Mn. Then here Fs is the shear force, A is the area of cross section above Mn. Above this Mn line, this is area of cross section. You have to, they will give, don't worry. Y bar is distance of CG of shaded area. Y bar is distance of CG. CG is the G point. For this shaded area, G is the CG point, and from neutral axis the distance is y bar. And I is the moment of area entire cross section above neutral axis. NA is our neutral axis, and B is the width of cross section at the level of MN only. Here width of cross section is B. This is very important. Tau S is inversely proportional to B. For rectangular beam, shear stress it will come like this. And for average shear stress, this is green color, this is average shear stress, tau AVG. And this is maximum shear stress, tau maximum. For rectangular beam, tau max by tau AVG. This is very important. So many times they asked in IAS and other examination also. ISRO also they are asking this question. 3/2 tau max by tau AVG for rectangular beams. It's 3/2 or tau max equal to 1.5 tau AVG average. Maximum shear stress is 1.5 times of average shear stress. Then for circular beam, circular shape, this is neutral axis, it will come like this. Tau maximum is here, tau maximum. And for circular cross section, tau maximum by tau average is 4/3. This is also very important. And for triangular sections, for maximum shear stress, this is also very important. This is CG point and this is midpoint, or this height is h/2. Here also h/2. Here shear stress diagram, it will come like this. Maximum will occur at midpoint. At neutral axis, this is neutral axis and this is midpoint line. Maximum at midpoint. Shear stress is maximum at midpoint. So here tau at neutral axis. And for triangular section, maximum shear stress is not developed at neutral axis, it is developed at midpoint. Tau max by tau average, it's 3/2, same as rectangular cross section, but tau average value is different here. I already told formula is tau equal to FA y bar divided by IB. This one no need to remember for ISRO, just remember this one. For IAS, This one also you have to remember. So tau is inversely proportional to b. B is the width. See, here b is more. In this area b is less. So tau is inversely proportional. From 4 options, shear stress diagram they will give. From 4 options, you will get somewhere in this area with less shear stress, and after that shear stress will increase. Here it is maximum. So see, here width is more from here to here, so shear stress is less. Like that you have to choose from the options. Wherever width is more, shear stress will less. In this type of beam, see, from here to here and from here to here, width is more, so this area you will get less shear stress. It will come like this. So you remember, tau is inversely proportional to b. For stress at a point, one more thing is I forget to tell. Here, independent stress components require. That question also they are asking, IAS and ISRO. So for 3D stress, because tau xy and tau yx both are same, so one you have to take either upper triangular or lower triangular, upper side of diagonal or lower side of diagonal. Total 6 stresses. Or 6 components require. Normal stress, sigma xx, sigma yy and sigma z. Then both are same, so you take 1, and from here and here both are same, so you take 1. From these two you take 1, so 3. Total 3 normal stress component and 3 shear stress component. Total is 6 component for 3D stress element. And for 2D stress element, number of independent components required is tau xy equal to tau yx. So you take 1. Total 3 components required, yy and tau xy or tau yx. Total 3 components required. Independent stress components. This one also they are asking. Require 3 for 2-dimensional stress, and for 3-dimensional stress independent stress components requires are 6. Independent stress component, it represents, it means for 3D out of 9 components, 6 components are necessary to specify a stress at a point, and for 2D out of 4 components, 3 components are necessary to specify a stress at a point. So independent stress components for 2D is 3 and for 3D it's 6. One more thing is important here. Number of strain gauges required. It's equal to number of independent components. So for one dimensional, number of independent components are 1, which is equal to strain gauges required. So for 2D stress, strain gauges required are 3, and for 3D stress, number of strain gauges required are 6. Thank you friends. Thank you for watching my video. Thank you.